All right, everybody. So welcome back. Today we'll be looking at a Leetcode problem called Implement Trie, otherwise known as a prefix tree. Now, this problem is unique in the sense that it deals with a data structure, or essentially we're being asked to create a data structure that is not very well covered, and not a lot of people use this, but I still think it's an important data structure to know because it is related to trees and graphs, and a trie is used in certain situations, especially situations that involve searching for words or prefixes in a more efficient manner. And so I still believe that even though it's not the most common data structure you'll encounter, it's still worth learning. So as the name of the problem suggests, we're going to implement a trie with insert, search, and starts with methods. So as you can see on the right, we already have the initializer. We already have a class called trie, the initializer, and then the three methods that were just mentioned. And so our goal here is just to essentially fill in the blanks and create a trie object that has all this functionality. Now, if you don't know what a trie is, we'll explain that in the conceptual overview, but let's just look at the example first. So we instantiate the new trie, we insert words, and then we search for them, check for prefixes, and then insert more words, and then search. And so in this case, apple, when you search for it, returns true because we just inserted it. But if we search for app, it returns false because we haven't inserted that word yet. And so again, I'll go into this in the conceptual overview because there's a special case you have to cover in order for a trie to know that you're dealing with a specific string. So in the second example right there, or when searching for app, it returns false initially, but you can check if a prefix starts with app, that will return true. And then when we insert the word app in there, when we perform a search on it again, then it appears. So again, I'll go into more detail in the conceptual overview. And then finally, there's a note at the bottom. So you may assume that all inputs are consistent of lowercase letters A through Z. All inputs are guaranteed to be non-empty strings. Cool, so hopefully this makes sense. And now we'll dive into the conceptual overview. So a trie is a unique data structure in the sense that it looks like a tree or a graph, but it could more accurately be described as an n-ary tree. So the roots can branch off into multiple different nodes and so on and so forth. It isn't constrained by values being smaller or less than the root, like with a binary search tree, or a root can have multiple different nodes. It's not just limited to two. And for the most part, tries will almost always deal with specific characters and strings rather than other data types. And so let's just look at an example. So we'll have our roots right here, which will just leave as an empty node. So I'll declare this as root, right? And let's say we want to insert the word apple. So we have apple. So let me just put that in there. And so, great, we have our word apple right here. Now, remember earlier how we were searching for the word app and it returned false initially? So one of the things with tries is you have to essentially put within the trie that you're dealing with a valid word, right? So when we input apple, so let me just look, putting apple here. So when we're inputting apple, this is what the visual representation of what it looks like in the trie data structure itself. But then when we get to the end E, how do we know this is a valid word? Well, since we inputted this word, what we can do is sort of input a value, like we can do a dash or a hashtag or whatever. In this case, I'll just put a dash. So a dash essentially signifies that we've reached the end of a valid word. And so let's input more values into our trie. And so similarly, we have apple. Let's try and put app. So app comes in. We already have an A, okay, and we already have a P, so we're good there. We also have another P right here, and so this is where it stops, right? But we have an L afterwards. But we know that we've inserted app, because so we know that's a valid word on its own. And so again, what do we do? Well, in order for it to determine that, or in order to determine if this prefix right here is a valid word on its own, we just simply add a dash. And so now if we're looking for app, we go app dash, okay, we found that's one word. But if we're looking for apple, We can go A, P, P, L, E. Okay, now we found another word. Let's continue with a couple more examples. So let's say I want to add the word code. So code would come in here. Since we're starting off with A and there's no C, then we will branch off over here and put C, and then we just continue. So we create code, right? And again, we have to signify this as a valid word, so I'll put a dash. And then to build up on this, what if we want to add the word cool? So I have code, cool. So C's already there, O's already there. Cool does not have a D, so we branch off. So cool. And so on and so forth. So as you can see right here, CO and CO are both shared by code and cool. And so when you're looking in a tree, there are words that will share characters, and so C, O, and then at this point the branches off, and so it can branch off into several different characters, and those can be used to construct different strings. So if we're looking for code, then we'll just look for a D and E and so on and so forth. If we're looking for cool, then we know to look for an O after the initial O right here. So we look at O and then L and then so on and so forth. And so if I were to input a lot of string values in here, this trie could, branch off into so many different possibilities, So tries can get very, very big and fill with a lot of different character values. The whole underlying goal of this data structure is just used to it's used for a retrieval of a key in a data set of strings. And so one use case for this data structure would be if you're working on an autocomplete, right? So if you're looking for, for example, the word apple, as you type in AP, other options might come up. So we might have app, we might have, maybe let's say we have ape. So if you're looking for ape, that could be one option. So just type in your Google search bar and try to visualize how the recommendations that come up might look in a trie. That might help you visualize this better. So that would be one use case. Another use case could be a spell checker. Let's say you're inputting a word. So let's just say, for example, you're trying to type out brown, but then let's say you misspell it. It's like BRWN. So maybe there could be an algorithm written that would check certain prefixes of the string. So if we're looking for brown, maybe we start with B, and then we start with R, and then W. Well, W doesn't lead anywhere, so maybe it just goes R, and then checks other options until we settle on O, and then W, and then N, right? And so by doing this, we can check the prefixes and sort of explore, different areas of our trie to find the proper word that you're looking for. So that could be another use case with spell checking. All right, so this is an overview of what a trie does. We've explored inserting, as we put apple, app, code, cool, and then we've explored searching, so search. And so searching means we're looking for the entire word, not just a portion of it. If we're looking for a specific portion, in this case, that would be called a prefix, then we'll have a function called starts with. And so starts with would be, let's say you're looking for the word cod, right? So you're looking for cod. Well, we have code right here, but cod is still its own prefix within the tree, so this would return true. Okay, so we've explored all the main functionality. Now I want to look at how we can represent this in code. So before we actually jump into the code, we can represent this a number of ways, but I'll show you one that I think is the easiest to understand. Okay, so there are a number of ways to represent a trie. One way you could do it is with a trie node. And a trie node could have a bunch of data. It could have, the value itself, so whatever character is stored at that node. It could have characters. And so characters would be all the other nodes that it points to. So it could be like another trie node. So it points to other nodes. We have a value that denotes whether it's the end. So we could just say like valid string or something. This could be a Boolean. So if it reaches the end, we could say true Like for example, if it's a dash, then we know it's reached the end, so that could be a signifier that this node is part of a valid string itself. And this is fine, we could do that as well. Another way that we could implement a trie very cleanly and simply is by using nested dictionaries. Let's look at the values that we previously inserted into our trie. So let's say we're trying to insert code, right? So the way that would look in a dictionary could be we have the individual character. So we start off with C. We input C right here. And then C is a map, right? And so what do we put in there? Well, C contains O. And so O would have its own mapping. And then we go to D. So now we look at D. And then that has its own mapping again. And then we look at E. And then E also has its own mapping. But then within E, because when we input the word code, this is the full word that we want to input. And so we know that this is going to be a valid string after we input it. So then we have to declare that again. So then we have to put the dash here with the value of true to signify that code is in fact a valid string. And so what this will look like is in the very last value in E, we'll come here and we'll put a dash string with the value of true. So again, this means that the word code is valid because we have this right here. Cool. So now, speaking of cool, what if we want to actually add the word cool? So if we want to add the word cool, well, we already have a C, right? So there's no need to go and add another one. We already have an O, so again, no reason to add another one. But this is where our paths diverge. So let me come down here. Hopefully I have enough space. And so E is closed off. O is pointing to another O, right? Because we have C, and then C has O in it, and then O, because we have code previously input, D, the character D is within O right here. But we're going to do something similar. So O will actually be within O. So we have D, and then we have O right here. And so this O is within this O's mapping right here. And then the logic continues. So then we have O, which is a map. And I'm running out of space here. But then within O, we have L, which points to another map. And then within L, we have finally our dash, which signifies that cool is a valid word. All right, so let's take one final look at how a trie would be represented with nested dictionaries. And so if we look at our example, we have 3 strings, right? We have app, ape, and apple. And so what this would look like in a trie representation is, let's say we have app put in first, right? Or sorry, ape. Let's just start with ape. So we put in our A, and then within A points to a P, and so we have P, and then P points to an E, and then so ape is one valid word, right? And so then we have our final dash, which we set to true, because ape on its own is a valid word, right? And so, cool, now we have ape out of the way. So what if we want to put app? So with app, we already have an A in there, so we look into that. We already have a P, so we look into this. And then within the P brackets right here, we can see that there is an E within P right here, but there's no P yet. So what we would do is we would come down here and put a P. So this P is within this P right here. And so now it's A, P, P. And so now we have app. And since app is its own valid word, then we would put the dash to signify that app right here is a valid word on its own. Okay, and then finally we have a bigger word. So now we have apple. So again, let's go through. We start from the root and then we look, what do we have? So there's an A in here, then we have a P, And then since we have already input app right here, if we look within P, there's another P, so that's set up for us. And then as we can see, we have this, but then we also have an L alongside within the nested P dictionary right here. And so the value of L will not point to an E. And then since apple is a valid word, we put a dash, a key value pair with dash and true. And so visualizing this, we know that apple is its own word. So hopefully this is all making sense. I know nested dictionaries can be kind of a pain to look at sometimes, but I encourage you to try and implement this approach by hand on a piece of paper and try inputting words, so you could try, I didn't put it here, but you can try code, cool, dog, doge, just try inputting it in there and seeing how it would be represented by a bunch of nested dictionaries and really try and understand how this approach works, because nested dictionaries is a very simple and straightforward way to implement this, and it just works. And I definitely view this a lot simpler than creating a try object, which you could implement with a try node object. And there's nothing wrong with that. I just prefer the nested dictionaries approach for its simplicity. All right, so now that we've implemented the nested dictionary try, let's look at runtime complexity. Since for the most part our try will just be looking, we either insert or just look for values. At most, the runtime will be, we could just say O of M. M in this case is going to act as the key length. So let's say we're looking for apple, apple's the longest one. So that would be like worst case scenario, because that means we have to look through 5 characters, or I guess 6 if you count the dash right here. And so that would be the longest runtime within this specific try data set. And similarly, the space for our try is also O of M. And that is just because we have to add up to M nodes. And so whichever value takes up the most, in this case, in our example, apple takes up the most, that would be O of M space. Cool. So again, hopefully this makes sense. I encourage you to try to implement this on your own. And with that being said, let's go look at the code. Okay, so now we're going to implement a try. And remember, in this approach, we'll be using a dictionary. So first things first, when we init this try object, we want to represent it somehow. So we've chosen the data structure hash map as the way to represent our try object. So we'll simply just say self.try equals empty dictionary. So from here, we can use this to be able to reference values as we insert, search, or starts with functions. So we can start building this up. So let's start with insert. What happens when we insert? Well, we insert a word. Essentially what we're doing is if the word or the character is not there, we just add it. If it is there, then we just go within that character's value, which is a mapping. And then if we don't find another character within that character, then we add the value and then continue as usual. So if we insert, the first thing we want to do is get access to our try. And then we want to iterate through our word. So for W and word, whatever word that is that we're inputting, what do we want to do? Well, if that particular character is not in the try, we add it. So it'll look like this. What we're doing here is we're taking the key. Remember, in the conceptual walkthrough, if we have, let's say we put O within there, then the value gets set to an empty hash map. And so we do this for every character, but then if this check, whether this check passes or not, we set our current value that we're looking at to the one in our string. So that'll be t equals tw. So essentially, this just moves through our try. If we encounter C, this becomes C. Then if we encounter O, this becomes O. If we encounter another O, this becomes that O, and so on and so forth. This is just a way for us to move through our tree. We just set T, the dictionary that we're looking at, to T of W. And so since we're inserting, remember, if we insert a valid word within our try, then we just return, or sorry, not return, because this function doesn't modify anything. We add the dash And this could be whatever, it could be a hashtag or whatever. For me, I'm just choosing a dash for simplicity's sake, and I'm setting that to true. What this will look like is if we add, let's say for example, the word cool, it'll go through and it'll put C because C is not in there. So then we have O, and then it puts O because it's not in there. And then we're looking within the O mapping and we add another O. And then within the O mapping right here, we put L, and then within the L mapping, we put a dash. And then we set that to true, so that'll be true. But anyways, I explained this a little bit more thoroughly in the conceptual walkthrough, so if you're having trouble understanding this, just look at how I visually represented it in the last section. Cool, so this is pretty much all there is to the insert. You're just adding characters that are not previously there. If they are there, then just move on, and then at the end of everything, add a dash. Let's look at search. So similar pattern, we say self.try, we want to get access to our actual try structure, and then we say for w in word. And most of these functions are going to look very similar. They're only slightly modified functionality. So we're still iterating through our word string. And if w not in t, so if we're searching for a word, if we find the specific character that we're looking at is not within the data structure, then obviously the search fails, right? So then we just simply return false. And then again, we just move on. This is the way we move through our tree. So we're just going down further within the nested values to move through our tree structure or our try structure. And then at the end of everything, we return if the dash is in T. Because if the current mapping we're looking at contains a dash, then that means that we've reached the end of the word that we're looking for. So we know that this is valid. So if this is within the current mapping that we're looking at, so again, if we reach the end of a word and our mapping has this, then we return true essentially. Cool, so that looks good. Now finally we have starts with. So starts with just checks if a particular prefix can be made with the data already within the try. So t equals self.try for C and prefix. We will again check if C not in T. If it's not, just return false. We must move through our try. And if we find what we're looking for, essentially if we go through the entire prefix and don't hit false, then it's just implied that our prefix is in there, so then we just return true. And yeah, that's all there is to it. I mean, we have our mapping, we look for, or we insert characters into our maps, creating nested maps that each hold characters that point to other characters, or dashes which contain, or which indicate that the characters so far, or that the string that we've gone through so far is in fact valid or not. We have a search, so we can just determine if the word that we're looking for is within our try, and then starts with just looks for a specific prefix. So this all looks good, so I'm just going to go ahead and run this and see what we get. Oh, whoops. I put a dot right here. Self.try. Okay, mistake. Awesome. So we get the appropriate value that we're looking for. So now let's try our luck by submitting it. Yep, and perfect. 96.64%. So this is a very fast implementation. It's simple, again, uses the hash map. So super simple approach. The logic is very simple once you understand it. The try data structure isn't that intimidating. I know maybe people haven't had much experience with it, so maybe they find it a bit scary. But honestly, it's not that difficult. Once you know exactly what a try does, you can sort of harness its power and easily implement it. So it's not that scary. But again, I like this problem because even though a try is not used, or is not very commonly used within coding interviews, a try data structure is powerful because it is used in a lot of real world systems. So for example, Google probably uses a try with their autocomplete, right, in the search bar. Lots of programs use some form of string correction. So if you make a mistake typing, there's probably an underlying try structure that will fix your mistake. Or tries, I believe, are even used in like cell phone companies. So think like T-Mobile, they probably use tries like hold some key data related to phone numbers or something of that sort. So there's a lot of real world implementations of a trie data structure. So just knowing how to implement it, knowing how to interact with it, even at a base level, is an advantage, I think. So hopefully you learned a lot. Make sure to study up on this data structure, and I will see you guys in the next one.